All right, this is section 7.5, using the Pythagorean theorem. So now that we've worked with the Pythagorean theorem, we know a squared plus b squared equals c squared. We're going to use the Pythagorean theorem more than just to find the side lengths of triangles. So the first thing we can do is we can reverse the statement around. And so this is called the converse. The converse of a statement switches the hypothesis and the conclusion. So if P then Q becomes if Q then P. So what we're going to look at a few different statements and see if we can write or think of what the converse of that statement is and see if it's true, because not every statement is true when you reverse it around. So the first one we have here says, if A equals B, then A squared equals B squared. And so the converse of that statement, if you switch those if-then statements, it would say, if A squared equals B squared, then A equals B. And that's actually not true. This would be false. And so I can give a counter example or a counterpoint to that. When you take 1 and square it, you get 1. When you take negative 1 and square it, you also get 1. So when it says, now I agree that this statement is true. The original statement is true. But reversing it around to say that a squared, if a squared equals b squared, then a and b must be the same, isn't true, because a could be 1 and b could be negative 1, and those two are not the same. So the original statement true, but the converse of that statement would be false. So in order for it to be true, it'd have to be true every single time. Example B is similar to that. It says if A equals B, then A cubed equals B cubed. Now this statement again is true, but we're going to think about the converse would say, which says if A to the third power equals B to the third power, then A equals B. So to use the same two numbers we were looking at with the 1 and the negative 1, if I have 1 and I raise it to the third power, I get 1. If I have negative 1 raised to the third power, because it's an odd exponent, negative 1 times negative 1 times negative 1 is negative 1. It doesn't become positive because I'm not squaring it. It's not an even exponent. So this one is actually going to be true. The converse of this statement would be true, because if A cubed equals B cubed, then the original numbers A and B must be the same, because it is an odd exponent. So we're not going to see what happened up above with the even exponents giving us two different answers, or giving us the same answer for two different numbers. Example C says, if one figure is a translation of another figure, then the figures are congruent. Now this statement is obviously true. All these statements are true. Let's see if the converse would be true. If the figures are congruent, then one figure must be a translation of the other. And that would be false. There are several different types of congruent transformations. Now, I agree, again, if it's a translation, of course they're congruent. But if I flip the statement around, the converse of the statement says, if they're congruent, it must be a translation. No, it could be a rotation. It could be a reflection. All right, so when I flip the statement around, it doesn't remain true. And the last one here, example D, if two triangles are similar, then the triangles have the same angle measures. I agree with this statement. Let's see if the converse would be true. If the triangles have the same angle measures, then the two triangles are similar. That is false. If I flip it around, it would be false. If the triangles have the same angle measures, they could be similar, but they could also just be congruent and have the same exact side lengths as well. So I agree that if two triangles are similar, then the triangles have the same angle measures. I agree with that, but if you reverse it around, if the two triangles have the same angle measures, then they must be similar. That's not always true, because they could be congruent triangles. So again, when you take the converse of a statement, it doesn't always remain true. So what about the Pythagorean theorem then? The Pythagorean theorem, as we know, says that if a triangle is a right triangle, so if you have a right triangle, then a squared plus b squared equals c squared. The converse of the Pythagorean theorem, if I flip those statements around, would say that if a squared plus b squared equals c squared, then you have a right triangle. And the converse of the Pythagorean theorem is true. It's one of those always true statements. And so that's actually really interesting because instead of finding one of the missing side lengths like we normally do with the Pythagorean theorem, I can look at 3 side lengths on a triangle and determine if it is a right triangle using the converse of the Pythagorean theorem. So in this first example, again, if a squared plus b squared equals c squared, then I have a right triangle. So let's see if a squared plus b squared equals c squared. 9 squared is obviously 81. 40 squared is 1,600. And 41 squared is 1,681. So if I add these together, I can see that I get the same exact thing on both sides. So again, if a squared plus b squared equals c squared, then I have a right triangle. This is true, so this must be a right triangle. So when you're working on your work papers, make sure you show at least this much work. I want to see all the way through. Make sure I can see that they're either equal or they're not equal. In example B, we don't need a picture of a triangle. We can still do a squared plus b squared equals c squared. Now, remember, c is always the longest side, the hypotenuse. So this must be a and b, or b and a, doesn't really matter. A squared plus b squared equals c squared. And let's see if this is a right triangle. 400 plus 441. And then 28 squared is 784. And then if I add these together, I get 841 equals 784. In order for this to be a right triangle, those would have to be the same, and they are not. So this is not a right triangle. Doesn't mean it's not a triangle. It just means it's either an acute triangle or it's an obtuse triangle, which we'll talk about in just a moment. So you heard me mention in the last video, we talked about Pythagorean triples. And so a Pythagorean triple is a set of 3 natural numbers. There's a word you should be familiar with, natural numbers, a, b, and c, where a squared plus b squared equals c squared. So basically 3 natural numbers that satisfy the Pythagorean theorem. They have to be natural numbers, so they have to be whole numbers, except obviously 0. So natural numbers are the numbers starting with 1, 2, 3, 4, so on and so forth. So there are very common Pythagorean triples that you'll see a lot. The first and most common is a 3, 4, 5 Pythagorean triple. If you have a right triangle with side lengths 3, 4, and 5, that is the most common type of right triangle, because obviously 9, 3 squared, plus 16 equals 25. All right, so that's the first and most common. There are some other Pythagorean triples, including the 5, 12, 13 Pythagorean triple, 7, 24, and 25, and then 9, 40, and 41, like we looked at in that last problem with the green triangle that we did just a moment ago. Now, there's a very long list of Pythagorean triples. This is by no means just the entire list. But what's interesting is that they also work in multiples. So if you see a triangle that's a 9, 12, 15 triangle, then it has to be a right triangle because that is a multiple of the 3, 4, 5. Obviously times 3, times 3, times 3. Or if I did a 6, 8, 10 triangle, that would be a right triangle. Or if I did an 18, 80, and 84, or sorry, 82, if I can do my math right, and 82. That would be timesing all these by 2, so that would be a Pythagorean triple as well. So the Pythagorean triples work in multiples, and there's a very long list of them. So if you're ever asked about, is this a Pythagorean triple? Well, if it satisfies the Pythagorean theorem and you're using natural numbers, then yes, it is. If it uses decimals or fractions, then no, it's not. So if a squared plus b squared equals c squared means you have a right triangle, what happens if a squared plus b squared does not equal c squared? Well, we know it's not a right triangle. So what kind of triangle would that make it? Well, we know, again, a squared plus b squared, if it's equals c squared, we know that is a right triangle. If a squared plus b squared adds up to be greater than c squared, then we know it's an acute triangle. And if a squared plus b squared is less than c squared, we know it's an obtuse triangle. And so here's how I remember this. It's all about c, right? If a squared plus b squared equals c squared, it's right. If c squared is small, that must mean we're working with an acute triangle. So if c is really small, then that would be an acute triangle, right? If c squared is bigger, or larger, greater, then that would be an obtuse. So if c is really big, that would be an obtuse triangle. So it's all about what c squared is. If c squared is the same, it's a right triangle. If c squared is smaller, it's an acute triangle. And if c squared is bigger, it's an obtuse triangle. Now, we have to keep this in mind, though. We've talked about how not all three sides make up a triangle. When we had the yarn out earlier and we were trying to figure out, why some three pieces of yarn would make a triangle and then three other pieces of yarn would not make a triangle. So the triangle inequality theorem does come into play here. If a plus b is not greater than c, then you don't have a triangle at all. So just be careful of that. Don't just automatically assume you always have a triangle. All right, so we are going to use the converse of the Pythagorean theorem to classify each triangle. So it's either going to be an acute triangle, a right triangle, or an obtuse triangle. For example A, we're going to say that if it were a right triangle, this would have to be C, right, because it's the longest side. If this is a right angle, I'm not really sure if it is or not. Kind of looks like it might be. So A squared plus B squared equals c squared. And again, I'm just writing out the same work that you would want to show on your work papers. 24 squared is 576. 36 squared is 1,296. And 42 squared is 1,764. I add up 576 and 1,296, and I get 1,872 equals 1,764. So it's obviously not a right triangle. So because a squared plus b squared is bigger than c squared, that means c squared is small. And that's what tells me and kind of reminds me this has to be an acute triangle. In fact, it'd be an acute scalene triangle because none of the sides are the same. But we can just say it's an acute triangle. For example B, if it were a right triangle, this would be C. 18 squared plus 12 squared equals 24 squared. 18 squared is 324. 12 squared is 144. And 24 squared is 576. So I'm going to add 324 and 144 together to get 468 equals 576. It's not a right triangle since c squared is bigger. Come on, there we go. Since c squared is bigger, then I know this has to be an obtuse triangle. In fact, it looks like an obtuse triangle. Be careful to make those judgments. I have found some problems here in the big ideas where they give you a triangle that looks like it's a right triangle, but then it's not. Kind of like this one here. Or a triangle that looks like it might be an obtuse triangle, but then it's not. So they're not always drawn to scale. So make sure you show your work to make sure you know if it's acute, right, or obtuse. Here we have to show our work because they don't even give us a picture. So a squared plus b squared equals c squared. And I know 25 has to be the c because the longest side there. So 225 plus 400, and then 25 squared is 625. Well, 625 equals 625. So this would be a right triangle because it is a it's not just a right triangle, it's also a Pythagorean triple, right? This is a multiple of the 3, 4, 5 Pythagorean triple that we talked about, so that is a right triangle. And then for example D, before you go and rush to judgment and just start writing this down like I'm doing right now, look at the side lengths. 7 plus 19 are the two shorter sides. has to be greater than 29 in order for it to be a triangle. Well, 7 plus 19 is 26, if I can write this down. 26, which is not greater than 29. So not only is this not a right triangle, this is not a triangle at all. Because, because it doesn't follow the triangle inequality theorem. These two sides are too short to connect with the long side. So double check, make sure that you're working with actual triangle measurements and not just three sides that don't even make a triangle.